Welcome to solverfy.
We know that the rate at which incident protons, for part A, the rate at which incident protons arrive at the barrier, n, would be 1.0 kiloamperes divided by 1.60 times 10 to the negative 19th coulombs, the charge of each proton. This would be equal to 6.25 times 10 to the 21st per second, so protons per second. We are going to let n times t, the number of protons arriving at the barrier per second, times the temperature, times the waiting time. This is going to be equal to 1, and we can then say that the waiting time would be equal to n times the temperature to the negative first. We can then say that the waiting time t is going to be equal to 1 over n multiplied by the exponential function. This would be 2L times the square root of 8 pi squared times the mass of the proton times the potential energy minus the total energy. This is going to be divided by h squared, or it's simply the potential energy minus the energy after the barrier. This is going to be close parentheses, and then we can solve for the waiting time for a proton. So essentially, for part A, t is going to be equal to 6.25 times 10 to the 21st per second, numerator 1, times the exponential function of 2 pi times 0.70 nanometers divided by 1,240 electron volt nanometers. And this would be times the square root of 8 times 938 mega electron volts, and then this would be multiplied times 6 minus 5 electron volts, close parentheses. We know that the waiting time would be 3.37 times 10 to the 111th seconds. This is approximately equal to 10 to the 104th years, which is much greater than the age of the universe. So an extremely long time. Doing the same exact calculations for an electron, except that now we're going to replace the mass of the proton with that of the electron. And what this is essentially doing is that the waiting time is going to greatly decrease, as you'll see. This would be 1 over 6.25 times 10 to the 21st per second, and then again times the exponential function of 2 pi times 0.70 nanometers divided by 1,240 electron volt nanometers. And then this would be multiplied by the square root of 8, and then this is where it changes. Instead of 938 mega electron volts, we have 0.511 mega electron volts, and then this would be multiplied by 6 minus 5 electron volts, and we have, close parentheses, the waiting time here would be 2.1 times 10 to the negative 19 seconds. This is a very short amount of time, and as you can see, the only thing that is changing is because the mass of the electron is much, much less than the mass of the proton, and that's why this waiting time greatly decreases. That is the end of the solution. Thank you for watching.